All right, so let's resume our discussion. And when we did this initially, we concluded that if we use this particular variable order and we set x1, x2, x3, then in that particular case, we end up getting 3 distinct subfunctions, and only one of them depended on x4, which is the variable that comes after x3. And if we use this particular variable ordering here, then after setting x1, x3, x5, we get 8 distinct subfunctions, and only 4 of them end up depending on x2, which is the variable that comes after that. And now we get to the punchline here, which is this theorem. And this theorem basically says the following. Let's look at it concretely and then we read it. Concretely, it says this OBDD, if you build an OBDD according to this variable order, then you're going to have exactly one node that is labeled x4. And if you actually build it according to this particular variable order, then you're going to have exactly 4 nodes that are labeled with x2. And if we look at it more generally, it says let this set Sj be the set of distinct subfunctions that you obtain by fixing x1 all the way to xj minus 1 to constants, like we did here, and that are also essentially depend on this particular variable. Then guaranteed the reduced OBDD for f under this variable order will end up having exactly that many nodes labeled with this particular variable. So it's all about subfunctions, and it's all about using a variable order that leads to inducing the smallest number of distinct subfunctions. All right. And someone mentioned the connection to our caching formula caching technique from last time when we talked about how we can cache when we're using exhaustive DPLL to compile OBDDs. And precisely that formula caching was trying to identify distinct subfunctions and not recompile them. But the connection is even stronger because the caching technique that we used there was really at the heart of it, trying to put a bound on the number of distinct subfunctions. And therefore, it's not only was a technique to make things efficient, but it was a technique that could be used also to bound the size of the OBDD based on this theorem. All right, folks. So this basically concludes what we need to say about variable orders and the relationship between those and subfunctions. What is left for us to do here is simply talk about what we can do with OBDDs as far as queries and transformations, and then we will have a summary table that tells us basically what's going on with OBDDs. And the story will end up being relatively simple in the following sense. We will look at 3 particular transformations on OBDDs. We won't be saying much about queries. Why? Because OBDDs are a subset of deterministic decomposable, and therefore also of DNNF. And they will inherit a lot of these queries. So you will see that there is a couple of queries that are left that will fill. But the main thing here we're going to be focusing on is transformations. We'll do 3 of them, 2 very quickly and 1 a little bit more. And then we'll be ready to go ahead and fill these 2 tables about queries and transformations that can be done in Polytime in OBDDs. And that would be the extent of what we need to say about this today. So let me start with one transformation that I want you to discover it for me. And that is negating an OBDD. And the claim is you can negate an OBDD easily. And I'm going to actually draw one for you. And you tell me what should I do to negate it. This is variable 1, and this node is labeled with variable 2, and this is 4. And that's what I basically have in this particular case. So claim is you can negate an OBDD easily. And then you guys tell me how to do that. Here's an OBDD. X1, X2, X4, high, low edges, and how do I negate it? Someone said, that's pretty easy. Actually, a couple of you said, just swap the sinks. Yes. If I just go ahead and make this guy the 1 and make this guy the 0, I'm done. That's the negation. Isn't that nice? Okay, very good. Yes, we can negate easily. Let's talk another transformation, which is pretty important, and that's what we called conditioning, an OBDD, on, let's say, just one literal for now. And that is if you had, let's say, the OBDD delta, we talked about conditioning it on X or conditioning it on not X. Now, I have to mention here before we talk about this, that in this literature, the engineering literature, and definitely the original paper on OBDDs, talks about restriction. They use the term restriction instead of conditioning. So you would say restricting the OBDD, all right? And since we're talking about functions, you will see basically the notation. Sometimes people would say, okay, condition on X equals 0. Now, in this case, 1. Condition on X equals 0. In this case, sometimes they will write F, and here would be X equals 1, or F of X equals. You will see all of these things. But restriction is an important term to remember because that's commonly used there. Well, let's see that. Here I am, and here's the concrete example. Let's do it on this one. Let's call this guy delta. So this is my delta. So this is OBDD delta. And now I want to restrict delta on x2 equals, let's say, 0. Now remember, when we're talking about transformations, I want the result to be of the same form. So I have an OBDD. I want to condition it on not x2, or I want to restrict it on x2 equals 0, but I want the result to be an OBDD as well. So what do we do in this case? And someone is saying that what I need to do is basically convert node to high child and low child. Yeah, so look, what's going on is this guy. I'm saying this could be either 0 or 1. No, I want to restrict it to the 0 case. So what does that mean? Anytime I'm coming here, I'm not testing. I'm always going this way. All right? Well, so what do? It's easy. Anytime I come here, I'm not trying. I'm always going this way. Well, then I remove this test, right? And then what do? Then I direct that guy directly there, okay? So in this case, and people are saying redirect incoming arrows towards the low child, and that's what we did. And that's an OBDD, right? If we just did this, it may not be reduced. So we can do deletion as people are saying in this case, fine, but you guys get it. If I'm restricting on x2 equals 0, I remove that node and redirect its parents to its low child. If I'm restricting on x2 equals 1, the same thing. I remove that node and redirect its parent to the high child. Done. So if we want to use our notation from before, we would say that for OBDDs, I can negate in Polytime, I can condition in Polytime. And now we get to the next transformation, which is considered to be a big highlight of OBDDs, and you'll see why. And that is that you can take two OBDDs and combine them using a Boolean operation, like conjoin them or disjoin them in Polytime. And that has a lot of implications. And that procedure that we're going to discuss next, which allow you to do this, regardless of what the Boolean operation is known as the apply operation. We'll see. You'll see it's pretty simple again, and we'll see what the implications are. So, okay, we did negation, conditioning. Let's go ahead and do what people call apply, which is combining two OBDDs using a Boolean operation. We will start by making it concrete, where we talk about conjoining two OBDDs. So if you give me two OBDDs, let's call them F and G. And what I want to do is construct F and G. Doesn't have to be conjunction. Whatever we're going to say now, we're going to say will apply if you stick any Boolean operation there, but let's just start with that. Okay, folks, it's this is a very famous algorithm we're going to talk about next, and it's based on a very simple principle. And that principle is what we talked about before as the Shannon expansion. We also refer to it as Boole's expansion. And the idea is very simple. Pick a variable, x, and I'm interested in this guy. I'm going to treat it as one big function h. And if you remember, we can go and say x and f and g given x, or not x and f and g given not x. Remember this guy? So if you view this whole thing as the function h, we're just doing what we talked about before. H equals h, and okay, I keep switching notations on you, but I think you can manage. Right? That's what we did before. It underlies many things we talked about. We just did it, but instead of h, we plugged in f. Okay, that's what we're gonna do. This will do it. This equation will show you now how you can conjoin, disjoin two OBDDs in Polytime. And actually, it's more than Polytime. We'll make that more specific. The trick, though, is the following. The trick is this variable that we're going to use, x, is not going to be arbitrary. Remember, this is an OBDD, this is an OBDD. And they both, the requirement here, we should have spelled it out, they both use the same variable ordering. Okay, they both use the same variable ordering. So we're going to pick x to be the variable that appears first in either of these, right? And then we're going to do this expansion. So let's see what happens. You end up really looking at only two cases. The first case is that I do have f looking like this. I have the variable x and high child, low child. Let's call this f1 and let's call this f0. Okay, this is OBDDF. And let's look at OBDDG. This starts with x, this starts with the same variable. And then I have the high and low child. Let's call this G1, this G0. The other case we'll have to look at is that they don't start with the same variable, right? So we may have, in this case, the first guy starting with x, and then this is f1 and f0. This is f, and then the other guy starts with some variable y. That's possible. And then in this case, this is G1, this is G0. We just have to look at these two cases, right? If you're arbitrary OBDDs, either, and they both respect the same variable order, they either both start with the same variable order or they don't. That's it. These are the two cases. And I want to conjoin these two guys, and I'm going to use this formula. Let's look at what this formula does in this case. What happens? This says you want to conjoin these guys, do the following, right? Take the conjunction, conjoin, da, da. Let me simplify this one more step. And the one more step is the following. X, and now I'm restricting this on that. That's the same as basically restricting f on x and restricting g on x. And here, what I have is f restricted on not x and g restricted on not x. Okay, let's now evaluate this, what this guy is telling us about how to compute this conjunction. In this case, what happens? So help me out here. What is f restricted on this? Type something. Remember, this is the high child. We call it f1. The low child, we call it f0. What is f restricted on this guy? People are saying f1, correct? And similarly, g restricted on x would be this, da, da. So I can basically now substitute. And in this case, what does this guy tell me? This guy basically tell me that f and g equals da and f1 and g1, or da and f0 and g0. Okay, look now how beautiful this is. What is this? This is the decision node. Let's put it in red. The decision node labeled x. This is the high child, low child. And then what do I have here? F1 and G1. And here I have F0 and G0. That's basically what this guy says. If you want to conjoin these, that's the result. Why is this good? Because look at these guys here. what are these guys? How can I do these? How do I handle these? Right? This guy says, you want to conjoin two OBDDs that look like this? That would be the result. Okay, but says, fine. I mean, that doesn't give me the OBDD. I still have to compute this and compute that. Right, I do basically a recursion. I use the same algorithm recursively, and that will be well-founded because remember, F1, G1, F0, G0, all gonna be smaller pieces. And that's your algorithm. Look at the second case. The second case, what happens here? I have F and G. What does it evaluate to? Help me out, guys, here. Now, here you have to make an assumption. So X and Y are not the same, but let's assume that X appears first in the order. So this is first, and then this comes second. So what does that mean? That means, can X ever appear in this guy, in this OBDD? I have a total variable order, X appears first. And people are saying, no, you cannot have X appearing in this OBDD. So let's simplify now this similarly like we did here. So what do you end up getting? You end up getting X n. Now, F given X, we're going to get F1. And now G given X, what's going to happen? G given X is what in this case? I'm restricting this on X. X does not appear. What do I get here? I get G back. Excellent, guys. And now what do I have? Not X and here basically I have F0 and G. Well, what does that mean? Let's look at the picture. Same story. You basically need to have a node. Why am I not getting the red? Okay, so I'm getting this high child, low child, and except in this case, I'm getting F1 and G, and here I'm getting F0 and G. And same story, I can handle these using recursive calls. Okay, so if I want to write it, I would say conjoin again. We're writing the function conjoin, recursive call, conjoin here, and conjoin there, conjoin there. That's it. This is basically the skeleton of the algorithm. We're going to write the Zudo code, and I'll tell you why, because there is a couple of things we need to spell out there. But that is basically the algorithm. Now, we're calling it conjoin now. When we write the Zudo code, after making an observation about complexity, when we write the Zudo code, we're going to call it apply. And we'll not only pass it to OBDDs, we're going to pass it a Boolean operation. So it could be conjoin, disjoin, and it will work. But before I do this and show you the Zudo code, we need to make an observation about the complexity of this algorithm. And the claim is, if your first OBDD had size n, so let's put size here. This is n and this is m. That is the number of nodes in each. In an OBDD, we measure the size by the number of nodes. The claim is the complexity of this can be made. If you just do what I did, it's not going to be that, but can be made big O N M. So you can actually have a version of this algorithm that has quadratic complexity big O N times M. Now, there is a secret for doing this. If you just go and implement what I just told you here, here's the recursive cases. And of course, the boundary conditions is when you hit sinks, and we'll see the Zudo code, you're not going to get this complexity. But the claim is you can get this complexity. And the main observation is to say something about the recursive calls. Every recursive call will have a certain property. Remember, what are we doing? The function is conjoin that we're implementing here, and it has two arguments. If you make an observation about these two arguments, that gives you away the complexity, or how you can get this complexity. The main observation is the arguments to this is always a node in the first OBDD. And the argument here is always a node in the second OBDD. Look at the recursions, right? This guy here is always a node in the original OBDDF, and this second argument is always a node in the second OBDDG. Therefore, how many distinct recursive calls can I get based on the identity of their arguments? N times M. And the idea is, if you run the algorithm, as I just told you, some of these recursive calls may be made more than once. repeatedly. So what you need to do is have what we call a cache. And this cache, every time a conjoin is made and finished, it will go and put it in the cache and say, I already conjoined this with that, and here's the result. And then before you try another recursive conjoin, you first check, did I handle this one before? If yes, you return the answer. If no, you make the recursive call. That version of the algorithm then has this particular complexity, and we're going to write the code next. And the reason we're going to write the code, because you'll see how simple it is, and then we're going to add a little bit to it to make sure that the output is also reduced. Not only do I want to conjoin them, I want to combine them using any Boolean operator, and I want the result to be reduced. And let's go ahead and write it together. And then we'll be pretty much almost ready to wrap up. So let's go ahead. And there was a question about the size. The size is the number of nodes in the OBDD. Just count the number of nodes in the OBDD. Yes, the number of decision nodes. All right, now we get to the famous apply operation that OBDDs are known for. And even though, why was it called apply? Because this was the name, I think, Randy Bryant, who wrote this milestone paper in the 80s about OBDDs, called it apply. And it is a function that takes basically two things and then an operation. Let's do it star. It could be conjoin, disjoin. And the idea is we'll apply this operation to these two guys in Polytime. And then later it became known beyond OBDDs. So you say, I have a representation called ... And then people say, do you have a Polytime apply operation for it? And the reason why the existence of an apply operation is so important, one of them is that it is important for bottom-up compilation, which we're going to talk about later. So here's what we're doing. We're building this function apply, BDD, OBDD, OBDD, and a Boolean operation. And an OBDD is represented by its root node. So here's the cases. The boundary case, if these guys are sinks, then we know what to do. We simply return, we apply the operation to them and return, and we're done. Else, all right? Now, the first thing I want to do is see if I do have that in the cache. So did I handle this combination FG? Is it in cache, right? And if yes, then return cache of F comma G. Okay, this is what we talked. Else, let xi be first variable in FG, right? This is what we did. And now here's the recursive calls. I'm going to call this H, then go ahead and do apply on. I take F restricted on X, I equals 1. I take G restricted on Xi equals 1. And I do this recursive, and then I do the low. Same story, except now I'm restricting on Xi equals 0. And then I'm restricting this guy on Xi equals 0, and I'm doing the recursive call. Okay, that's pretty simple so far. Now, here's the stuff that I'm going to be adding to make sure that we're going to get a reduced OBDD. Remember, how do we lose having a reduced OBDD, or how do we end up having redundancy? Remember, deletion rule and merge rule. Tell me something that comes up here. So if I go and just say, okay, now construct an OBDD node labeled with this variable and having this as its high child and this as its low child, I may end up having a redundant OBDD, right? Because I may end up constructing opportunities for deletion and merging. Can you tell me what is the condition on these guys that I have to check to avoid having nodes that can be deleted? What I did is I'm already now constructing basically the node that is labeled with Xi, and this is its high child, and this is, I got the high child and the low child. I'm about to go and say, build this node. This is the high, this is the low child. I didn't do that yet, but I'm ready to do that. I've got the two children, I've got the variable, I made the recursive call, I'm ready to put this thing together. And I'm saying, no, be careful here. You don't want to just do that because you may end up not having a reduced OBD. Okay, good. And people are saying, if H equals L, you don't want to build this guy, right? Because that's going to be redundant and you're going to have to delete it. So now we put this first condition here and we say, if H equals L, then return one of them. And let's say, okay, good. Now, there's one more thing to do here, which is merge rule. Merge rule, remember, says you have this guy, but you have another guy exactly like it that you've already constructed, right? It has labeled with XI, has this as the high child, and has this as the low child. And to avoid being in a situation like this, what OBDDs do, you have another cache. And that cache basically keeps track of every decision nodes that you constructed. And they call that cache or that hash table, they call it the unique node table. So the idea is I need, instead of constructing the node immediately, I will go to a guy and I say, look, I need a decision node that has this as the variable, this as the high child, this as the low child. You've got one of these already? If you've got it, give it to me. Otherwise, please do construct one for me and give it to me and put it in your unique table. So what we do here is we end up writing node equals, and we make a call to this unique node function. And I'm telling it, look, I need a decision node that has this as the variable, that has this as the high child, this as the low child. And remember what this guy does. First, it checks, does it have one of these guys? Then it returns it, a pointer to it. Doesn't construct a new node. Otherwise, it constructs one, return it, and put it in the cache. Okay, we're basically done. Now that we have done these guys, then you go and say, okay, let me put in the cache that I already conjoined or applied the operation to F and G, and the result was this node. And we finally return this node. Done. Okay, stare at this very simple piece of code. We'll take two OBDDs that use the same variable order, apply a Boolean operation to them, like conjunction or disjunction, and gives you back a reduced OBDD in a time complexity of big O M times N, where this is the size of the OBDDF, and this guy is the size of OBDDG. Pretty nice and remarkable. This is the famous apply procedure for OBDDs. And we're now ready to go to the finish line here by doing the tables for operations and transformation. And you'll see now we pretty much have everything we need to fill that table pretty quickly. And you will help me with that. There will be just a couple of entries that we will not justify, but otherwise we're pretty much almost done here. There's a question about what if the two OBDDs have different variable orderings. This is a more involved topic because no, that's not easy. In fact, if you have two OBDDs that have different variable orderings, checking whether their conjunction is consistent is hard. By the way, the knowledge compilation map paper from 20 years ago that we put as optional readings have all of these things in it. Someone recently said that that has something like almost 350 results or something because it's all tabulated. It's an extremely a rich paper in terms of results, and you'll see something along these lines in there. So you guys check it out. There's also an update that I'll probably post later that resolves some of the questions there, strengthens some of the impossibility results. So, okay, let's go to the last step. And now what we're gonna do is look at both queries and transformations. This should be fun. We're gonna fill these two tables And if you remember what these guys were, I'm gonna go ahead and put them. We talked about consistency. We talked about validity. We talked about causal entailment. We talked about implicants and equivalence testing. We talked about sentential entailment and counting, and finally model enumeration. And here we have conditioning, whether we can condition a single variable for getting, and then multiple variable for getting, that's a single existential quantification multiple, arbitrary conjunction, what we call bounded conjunction that conjoin only a fixed number of things, arbitrary disjunction, and the bounded version, and finally negation. Okay, this is what we talked about. And now we're going to go ahead and fill these things. It's going to be relatively quicker than you think. The first thing we're going to do is we're going to look at queries and say, wait a minute, what do we already know? OBDDs are a subset of DNNF and deterministic DNNF. So any query that can be done on these guys efficiently can already be done on OBDDs efficiently, right? Because OBDDs satisfy those properties and more. And that immediately gives you this guy, and this, and this, and this, and this, and that. All of these are just inherited because OBDD is a subset of something we already discussed, and that thing can do all of these in Polytime. So we're only left with these two guys, and we'll get to them. The other thing that I'm not going to discuss is impossibilities, and that is I'm going to put them here. And as we discussed before, this is going to be a solid no, just no, not conditional anything. You cannot existentially quantify an arbitrary number of variables from an OBDD. You cannot conjoin an arbitrary number of OBDDs in Polytime, and you cannot disjoin them either. I'm not going to justify these. If you're interested in the arguments, you can check the knowledge compilation map paper. But now I'm going to go to the rest of them and show that all of the others can be done in Polytime. Okay? All of the others can be done in Polytime. So let's start with the simpler ones. Conditioning, we showed that. No, we showed a constructive way of conditioning an OBDD so it can, where we can do this efficiently. Negation, we showed that. Just swap these things. Let's do, what about this guy? We already showed the apply, right? I can take two OBDDs and conjoin them or disjoin them in Polytime. In quadratic time. Now, as long as I'm doing a fixed number of them, that's still Polytime, right? So if you take 3 of them, that's basically, becomes a cubical. But as long as the number is fixed, it's Polytime. So I know this and I know that done. What about variable forgetting? I'm claiming that that can be done as well, right? And let's see why. If you want to existentially quantify a variable from an OBDD or anything, what do? The basic definition, f given x or f given not x. That's it. Can I condition an OBDD on this guy? Yes. And the question was, is conditioning linear time? Yes. So I can condition easily. I can condition on the negation easily, and I can disjoin easily Polytime. So yes, that can be done. Why? Because of this and that. See, if you tell me you can disjoin in Polytime, you can condition in Polytime, then you can do forgetting one variable only from the basic definition. Okay? Okay, we're left with two more things now. These two guys, equivalence and sentential entailment. The simplest argument for equivalence is what we already discussed earlier, reduced OBDDs, right? You're talking about the same variable order here. And if they're reduced, you just do a pointer check. Okay, now I'm gonna do the last one here, which is what is sentential entailment? That you have delta 1 OBDD, does it imply another OBDD delta 2? Guys, help me with this. Because we're gonna do this and go home. Or, well, we are home, but so tell me how we're gonna do this one. The claim is I can do this. I can check, and this is gonna be none of the others allowed us to do sentential entailment. Now we're gonna be able to do it. And therefore, this is going to be the first guy we looked at that allows to do all of these and basically How do I test whether the claim is I can check whether delta 1 implies delta 2, both OBDDs using the same variable order? Let's see. And you need to use what's already on the board. There's a theorem. You guys should not forget it. Good. Someone mentioned refutation theorem. Refutation theorem is important. And someone else is also saying negate and conjoin. Very good. Refutation theorem. This is if and only if what? Delta 1 and not delta 2 is inconsistent. Okay, let's go to blue. So what do I need to do? I need to take this OBDD and what? Negate it. I know how to do this. That's pretty easy. Swap the things. And then I need to take this guy and conjoin it with this guy. I know how to do this, right? Apply. And then I get another OBDD. If that OBDD is consistent or not, that's something that can be checked easily. Duh. Now I can do this as well. Okay? So here we are. All of these 8 operations can be done in Polytime. And that's the first guy we looked at that had these properties. And we can do quite a bit, particularly this is exciting, that we can conjoin, disjoin, and negate. And there's a question about the difference between these two guys, this versus that. This is existentially quantifying a single variable, single forgetting. There is single existential quantification. This guy tells you you can actually existentially quantify an arbitrary number of variables. That is basically the difference between these two guys. Now, just one word on why is it exciting to have an apply operation? Because remember when we talked about knowledge compilers, we said there is top-down and there is bottom-up. We've seen the top-down ones. They are based on exhaustive search, like exhaustive DPLL. The bottom-up compilers work differently, and they need an efficient apply operation. They basically try to compile in the most obvious way, in the sense that if you have, let's say, a Boolean formula that says, you know, X or not B, and take this, and or W and dot, dot, dot. Okay, it will just go ahead and use apply and negate, which can be viewed as a special case of apply, and just walk bottom up on the formula trying to put things together. We will talk about this later because a little bit more intricate than it sounds. So bottom up compilers require an apply operation, and that's why it's important. Folks, we're done for today, and we'll see you on Thursday. Thank you.